Okay, so today is day 1 on the path to becoming real mathematicians. So this is finally the unit where you're going to write real life proofs. No, they're not going to be fill-in-the-blank proofs. No, they're not going to be matching proofs. No, you're not going to have a word bank. That's what we've done in the past. So we're not going to just throw you to the wolves. We're not going to say, alrighty, here you go, write a proof, have fun. We are going to take baby steps during this unit. Well, you have to be a mathematician. You don't have a choice. You're a math student. And I just think it sounds fancy to call you a mathematician. It makes you sound really smart, which you are. Okay, so what we're going to do is take baby steps onto the path of writing real mathematical proofs. Proof is just a way to show your teacher and show the reader that you understand what's going on. Because it wasn't just luck that you got side angle side. You understood the math behind why it's side angle side. That's why we do proofs. So let's take a look at today's first baby step towards proofs. What I'm going to do today is I'm going to give you a picture. You can write this down in your notes. You can draw that picture. Then I'm going to give you a statement that has a hypothesis and has a conclusion. The only thing you're going to do today is tell me why that statement is true. So I give you the hypothesis, I give you the conclusion, you tell me why. Tomorrow, I'm going to take something away. I'm not going to give you the conclusion. So tomorrow, I give you the hypothesis, you give me the conclusion and the why. And then on Monday, I take it all away, and you give me the hypothesis, you give me the conclusion, and you give me the why. So we're baby stepping, super fun, so that we can write proofs, take the training wheels off, and write proofs without assistance. Now, during this unit, you might want to have this paper out. It was on the calendar for yesterday, but you already got it in the triangle unit. If you lost this paper, print a new one from the calendar. You already know almost everything on this paper. You know most of these definitions, theorems, and properties. Anytime we come to one that's brand new, that you don't know yet, I will point it out. Other than the ones I point out, you don't need to memorize them because you already know them, you've already learned them, you've already used them. So don't be scared and be like, oh my gosh, I have to memorize this. No, you know most of this. You only have to memorize the ones that we haven't talked in depth about before. You'll see. Okay, so here we go. Let's start. We've got a picture. We've got a statement. If segment BD is perpendicular to AC,
do you write all of these examples?
You're welcome to, if you can write quickly. Yes, you're welcome to. If they're perpendicular, then angle BDA and angle BDC are right angles. So all we're doing today is deciding, why are we allowed to say that? Why are we allowed to say they're right angles if they told us the lines were perpendicular? So you can go look at your list. You can kind of get to know it and see if you can find one that matches the same hypothesis and conclusion we just came to. Do you see one?
Perpendicular bisector theorem.
We didn't cut anything in half though.
Right angle congruence?
No, we didn't say anything was congruent. Yeah, you said it in the, y'all said it in the chat. It's number 15. Everyone go look at number 15. If two lines are perpendicular, then they intersect at 90-degree angles. Do you see how the hypothesis and the conclusion matches? If, perpendicular, then, 90-degree angles. The hypothesis and the conclusion match word for word. So our answer is definition of perpendicular lines.
Isn't it also the definition of a right angle?
No, the definition of a right angle is if an angle is right, then its measure is 90 degrees. It's like that. Definition of right angle doesn't use the word perpendicular at all.
But the definition of perpendicular doesn't use the word right at all.
You're right, it uses 90.
So don't we connect the two definitions with 90?
If you want to get really technical, yes. I wouldn't focus as much on the conclusion. This is probably the only one this would happen to. I would just match the hypothesis perfectly, because the hypothesis is what you're assuming in the first place. So on definition of right angle, what we're assuming in the first place is right angle. We're not assuming perpendicular. So just match the hypothesis and we'll go from there. Thanks for getting so technical on me.
Thank you.
Okay, next one. If segment BD bisects angle ABC, then angle ABD is congruent to angle CBD. So our hypothesis is if a segment bisects an angle, then we get two congruent angles. What backs it up? What theorem, what property, what definition backs that up? Yes, number 19. So, it is definition of angle bisector. You can write definition of angle, and then this symbol right here means bisector. A little lowercase b with a circle around it means bisector, so you're allowed to abbreviate in that manner. The theorem literally says, oh, if an angle gets bisected, then there are two congruent angles. So we matched our hypothesis and our conclusion. All right, next one. BD is congruent to BD. We've been saying that for the past 3 days, but what property or theorem has been backing us up?
The reflexive property.
Number one. It's number one for a reason, because it's the most obvious and most important. Number one on your sheet, it's called the reflexive property of equality. I will accept just reflexive prop. I'm good with that. The reflexive property says that an angle or a segment is congruent to itself, which seems really silly that you have to say that, but you do. Okay, if D is the midpoint of AC, then AD is congruent to DC. What do you think? This one's number 10. It is definition of midpoint. Unfortunately, there is no mathematical symbol for midpoint. Why didn't someone make one up? Come on, get with it, people. All right, so definition of midpoint. On your paper it says, if B is the midpoint, then AB is congruent to BC, and that's exactly what we said in number 4. So I don't want you to be overwhelmed by this process. What I want you to notice is, see if this will play.
Oh my God, that's so creepy.
That's an easy one. The answer's in the question.
Did you hear what he said? The answer's in the question. I think it's more fun to say it when you make that hand motion. Look at this, guys. Look at these answers. If it's perpendicular, then blah, blah, blah. Oh, definition of perpendicular. If it bisects, oh, definition of angle bisector. An angle bisector right there. Midpoint, definition of midpoint. Midpoint, definition of midpoint. Normally, the answer is in the question. It's not a mystery. These are not going to come from out of left field. The answer is going to correspond and match up with the question most of the time. You're going to be reusing the same words you find in the hypothesis for the reason why. I want to do one more before we take our quiz, one more set of whys, but so you can just watch this one. You don't have to write this in your notes. Let's just do a little bit more practice, and then you can practice a lot more tonight on your assignment. All right, if segment AE bisects segment BD, so if this one bisects this one, then BC is congruent to CD. Definition of, what do you think?
Bisectors.
Good. Definition of segment bisector. You do want to say which kind of bisector, because there's a segment bisector, but there's also an angle bisector. So make sure you say which one it is. Yep.
Okay.
All right. BCA is congruent to ECD. This is one of the ones where the answer is not in the question. But if you don't know this one, yeah, if you don't know this one, you've been asleep for 2 months. You're welcome to abbreviate this one. You're welcome to just write vertical angle theorem. Very good. Oh, here you go. Here's your theorem we were talking about earlier. If B and D are right angles, then B is congruent to D. This is actually not the definition of right angle. This is one of those ones that I told you about, that I would say, hey, if something's new, I'll let you know, because that's like one of the only ones you'll have to memorize. This is new. No, we've never used this theorem before. See if you can find it on your paper. It's the same number as the day I was born on. You don't know that? No, not right angle theorem. You're missing a word. Yes, it is 17. So this is different. This is new. We haven't talked about it. It's called the right angle congruence theorem. It's not a definition, it's a theorem. It's pretty much a theorem that says, it pretty much says all right angles are congruent. If they're right angles, then they're congruent. That way we don't have to say they're right angles, and then we have to say they're 90, and then we have to say that their measures equal. We get to skip the steps. It's called the right angle congruence theorem. Okay, last one. If AB is parallel to ED, then
Click it.
angle A,
Gallery view.
angle A is congruent to angle E. This is another one where the answer is not necessarily in the question, but you definitely know this one from, we've been using it. What kind of angles are those?
Alternate interior angles.
Good.
Alternate angles.
So all you have to do is write the abbreviation for theorem after it. The alternate interior angle theorem says if parallel lines are cut by a transversal, then alternate interior angles are congruent. If parallel, then congruent. And it's called the alternate interior angle theorem. Okay?